See, well, this is really abstract. So what does this mean? So for example, ax less than or equal to b, or ax minus b norm squared less than or equal to 0, less than or equal to some constant c. So these are constraints, right? I can collect all those x's in a basket and I call that c, but all those x's should satisfy certain constraint, right? Like ax less than or equal to b. Is that fine? Okay,
Yes, sir.
so
Yes, sir.
equivalently I can say, well, this could be fi of x less than or equal to 0, hij of x equal to 0. This is the problem that we wanted to solve, right? So then we took two different approaches. Well, the first one that we looked at was Lagrange, right? What did Lagrange say? It said, well, you formulate this problem. So x lambda vector nu, right? So lambda has to be greater than or equal to 0 and solve a problem related to Lagrange. What was the problem? So you want to minimize the Lagrange with respect to x and maximize overall lambda and nu, where lambda is greater than or equal to 0, right? That's the problem. Is that fine? Is that okay? Everyone?
Yes, sir. Yes.
Yeah.
Yes, sir.
So this was the original constraint optimization problem. We converted this into Lagrange. So essentially you have to solve this problem, right? Minimize overall x, Lagrange of this thing, and then max overall lambda greater than or equal to 0 nu, right? This is what you had. There's no constraint on nu. Nu and lambdas are vectors. So this sort of converted this into an unconstrained optimization problem. Well, the only catch here is that this lambda greater than or equal to 0 is also a constraint, but that's not a big constraint. Like fi of x is less than or equal to 0 and hj of x is equal to 0. Okay, and the other catch is, you have a max min kind of thing. You have to maximize something and minimize something. Okay. Okay, so this is what we saw. We saw that if you solve this, you will get exact solution or the optimal solution if it is convex. If the problem is convex, this will give exact or the optimal, right? That's what it says. Okay, even if you don't understand the theory in detail, this is something that you should keep in mind. If the problem is convex, then the solving this Lagrange problem will, or this particular problem, okay, this particular problem, if you solve, it will give you the optimal solution to the problem. Okay, is that fine, everyone?
Yes, sir.
Okay. Now, oftentimes, so, well, what do you mean by that? So we looked at, so what do you mean by solving this problem, right? So we looked at what is known as KKT conditions. Remember KKT conditions? Go back to the lecture, whatever, and see what KKT conditions are. So we saw that if the problem is convex, solving KKT is essentially solving this quote unquote problem. That means if you find x, lambda, and nu that satisfies the KKT conditions, then that x that satisfies the KKT condition is the optimal solution. Okay. Just to summarize again, you could try to solve the original problem somehow magically. That is very difficult. You go for Lagrange. Then we ask the question: when is Lagrange? When will the Lagrangian formulation will give you the exact solution? It turned out that if the problem is convex, definitely it will give. Not necessary that all, there are problems wherein even if it's non-convex, still Lagrange can give you an optimal solution. But what can be guaranteed is if the problem is convex, then Lagrange will give you the exact or the optimal solution. So how do you solve the Lagrange? Well, KKT conditions, it's a set of equations that you have to solve. Now again, the question remains is, how do you find these solution to the KKT condition? It's a set of equations. How do you solve that, right? That's where we stopped, and we said we'll look at algorithms. Is that fine till now? You got it?
Sir, what was the use of dual that we studied, like dual of a
Ah,
function? Where is that used?
so for example, we solved some problems, right? A few problems wherein we could solve this dual problem exactly. Do you agree? Maybe we'll start with something today. What?
Sir, not Lagrangian dual, the one which we studied. I mean, where we could represent the function in a function of in the form of slope. I mean, y transpose x minus y x minus e to the
So
power x. That,
you are saying where did I use the Frenkel dual, right?
yes, sir.
Those kind of. Okay. So I didn't cover that. So essentially, I can look at this Lagrange. I can write the Lagrange in terms of the Frenkel dual also. So they are kind of related. So I can either look at Lagrange as some sort of a Frenkel or Frenkel as a Lagrange. So there is a relationship between the two which I didn't cover. So maybe that's the gap. Okay.
Okay, sir.
Okay, so right now, maybe I don't see that. If I had taught that, then it will become more too technical. So if you are interested, I can have a separate class just on that. Okay, connecting the two, so that whatever I taught about the Frenkel dual is not. You should not feel that it's useless, right?
Yes. Hmm.
Okay, so that connection is something that is missing. I agree. Okay,
Hmm.
Frenkel and there are a few other things also, right? So we looked at for example, cone. We looked at various other constraints and the duality there and so on, right?
Yes, sir.
So
Yeah.
you might be wondering where
So,
is it used,
so in the
right?
duality gap that you had explained,
The duality gap is kind of used, right? For example, if it is convex, the duality gap is 0. That means if you solve Lagrange, it will give you the solution, right?
okay.
That's what we said. I mean, I didn't prove that, but
Mhm.
I
Yes,
stated that, right?
yes, sir.
That is kind of used. But where is, for example, the cone, the dual cone, and all that, right? So I think in one of the optimization problem, the constraint was a cone, right? You had this cone constraint. Do you remember some A transpose X minus B norm less than or equal to some B transpose X minus B? Do you remember that?
Yes, sir.
So whenever you encounter such problems, the constraint set is like a cone, right? Now, how do you solve that problem? Well, it depends on your understanding of cone and in which direction you want to move inside the cone so that you will move in the direction of the descent, etc. Depends on the properties of that particular cone. Okay, again, it's difficult to cover all these things in one course. Okay, so maybe I'll see if at least cone is something that I can illustrate soon. Okay, so maybe before the course ends, I'll illustrate the cone. I'll connect some of these dots. Okay, is that fine?
Yes, sir.
Huh? I cannot connect all the dots because I think it will be heavily loaded. I'll connect some of these dots. Is this fine, everyone?
Yes.
Ah. So now I think we will. So what is it that these things are saying? So essentially, it's saying you have to solve some unconstrained optimization problem, right? So even the Lagrange says that you have to solve some unconstrained. So let's start with unconstrained optimization. See how to solve this. Oftentimes you can solve it using a closed form solution. In many other cases, there are no closed form solution, but you can solve it using some iteration. Okay. So let's look at the first unconstrained problem. So let's say I want to minimize overall x in the domain of some function f naught of x. So let's assume that this f naught is convex. Okay, so x is in the domain of this function. Now, what is the algorithm that you will use? So essentially, this is how it looks like, right? What is this? This is your optima, right? This is the optimal point, right? Let me call this as x star, and the corresponding value will be f naught of x star. This is the best, right? You take any other point, let's say x dash, then f naught of x dash is always larger than f naught of x star. Okay. Let's also assume that it is differentiable. So what is the algorithm? So you start at some point, you look at the slope there and move in the direction of the slope. Okay, so how do you write that algorithm? So this is how you write. Okay, so for example, you say that the first step would be you take the first point x1 to be equal to 0. Okay, so I'll start at the origin or some arbitrary point. Okay, of course, if 0 is not in the domain of the function, then 0 is not the right thing. You should probably take or some arbitrary point in the domain. Is this fine? So what is the next step? So you have to iterate, right? So the algorithm is basically an iteration. So you have 1, 2, etc. Maybe you do t rounds. So what is it that you will do? You will do the following, right? So now let's say z, I'll use a variable zt plus 1, which is basically this is xt. For example, if t equal to 1, x1 in this case is 0. So we'll start with 0 minus eta t times the gradient of f naught of xt. Is this fine, everyone? What is this called?
Gradient descent.
It's called the gradient descent, right? It's very easy. So it's called the gradient descent. Okay. And then what do you do? So it's after that it's n for. Then what is it that you do after this? Return. You can either return, for example, xt, capital T, or you can return, for example, the average, right? I can do the average. Okay, so xt, sorry, hey, why did I write z? I'll just write it as
xt plus
okay,
1.
xt plus 1 only. Okay, so this is xt, right? Or I can also do the following, right? So I'll take f of xt, f naught of xt. At each point, I'll see what is the value and pick the best. Well, this is of no use in this case because why? Well, you are moving the gradient descent direction, so most likely x capital T would be the least. Average also may not be useful because xt is the best, right? You better choose x capital T. Is this fine? This is called the gradient descent algorithm. Is this fine?
Yes, sir.
Okay. Okay, is this fine, everyone?
Yes, sir.
Okay. Now, this is an aside, but just to connect some dots, right? So what is it that you do if you have, for example, a problem like this, right? Let's see what are the possibilities. So for example, minimize overall x, f naught of x, subject to a constraint that x belongs to C. Okay. C, this is a set, well, it's described by some inequalities and so on. Depending on whether C is convex or not, we will be able to solve using Lagrange exactly or not, right? So anyway, so now let's assume that this is convex for a moment. Okay. Now, how do you solve this problem? Well, typically what do you do? So this constraint set could be like this, right? So this could be like fi of x is less than or equal to 0, hj of x equal to 0 corresponds to this convex set. That means I have to solve this problem, right? Lagrange x lambda nu. I want to minimize this with respect to x and maximize with respect to lambda positive and nu. Now, can somebody tell me how to solve this problem? So I have to solve this problem, right? So if I solve this problem, Lagrangian duality says that the x that you get is the optimal x, right? So how do you solve this problem? Do you agree that this is an unconstrained optimization problem? Yes or no? Yes?
Yes, sir.
Everyone? Okay. Now, how do you solve this problem? Huh?
So if we have this function, if it is like differentiable, then
Assume that it's differentiable, everything nice
yeah,
and cool.
mm,
Okay. Yeah.
yes, so then find its SUN and
Not
So
Hessian, right?
or
Huh?
KKT condition.
So we'll keep flipping, like we'll fix a lambda, minimize x using gradient
Exactly.
descent.
Right? So that's what this says, right? So what will I do if I were to write the algorithm? You fix lambda and nu and write a subroutine that will solve for x. Now you have gotten x, you take that x, fix x, solve for lambda and nu. Do you agree? Well,
Yes,
this
sir.
is intuition, right? So this is what I'll do.
So, but does that ensure that
That
the
is the
entire function,
question. Say,
like we can have Pareto solutions, right? I mean,
let's not worry about Pareto and all that.
okay.
So essentially, the our some theory that we learned gave us some algorithm, right? Now we have to build enough tools to see whether that is the solution that we want. That's a different, bigger question. Okay, but at least it gives us some algorithm. What is algorithm? Okay, so let's write that. Okay, maybe we'll write some pseudocode, right? So what will I do? I'll just take lambda 0. I'll iterate to 0 some lambda naught, nu 0. I'll put some nu naught, right? And x, sorry, I'll use cap. Okay, so I'll use small only. X 0. I'll use some x 0. Is that fine? This is where I start. Initialize. Right? And then what is it that I'll do? I'll fix lambda and nu and then iterate over x naught and x naught, right? So what is it that I have to do? So let's look at this, right? So you fix lambda. So how do I write this? So let me write, I don't know if I'll be able to write this properly. I'll try. So let me think. So first I have to write a for loop for x, and then for each x, I'll do a for loop for t, right? So let's do the following. For t equal to, I'll be careful here. Yeah, I'll use this only. T equal to this, capital T. Okay. What is it that I have to do?
So xt plus 1 is equal to
So
xt
now
minus
I
theta
have to basically I'll write this. Okay. So xt plus 1 is xt, right?
minus some
Minus eta t
del with respect
gradient
to
of L xt lambda.
lambda naught, mu naught.
Well, I have to have another for loop for lambda also, right? Do you agree?
Yes, sir. Like,
Okay. So I'll use that as k.
yes.
Okay. And new k. Do you agree? This is just the gradient update. Is this fine? Now, what should I do for this?
You need to put that inside another for loop for
Right? I have to
lambda
do
and
another
another
for
for loop.
loop. So what should I do? I'll do this. So maybe I'll do for. I have to do for k, right? K equal to 0. Well, what I'm going to do is
So not k. There should be a third variable
Yes,
outside
sir.
it.
for what?
Uh, Lambda and nu, they should be two different iterators like k or L. Not
No. Not for that purpose. So there should be two for loops inside one bigger for loop. So first x gets updated, below that lambda and nu get updated, and then this whole thing keeps repeating.
Yeah, so I'll write that first. Okay. So now I have to update lambda. So what should I do? Lambda k plus 1 is lambda k. See, this is a maximization
I
problem,
said
right?
plus would be there.
Plus, instead of eta, I'll use gamma k. What should I do? This is gradient with respect to x. This is gradient with respect to lambda
lambda.
of L. See,
X cap.
I'll have xt lambda k and then nu. Should I use k or yeah, this should be I don't know whether okay, so I'll just use this. Okay, what is the next step?
gamma k plus nu k
new
plus
k
1.
plus 1.
No, right? If it is negative, what will you do? See, if it is negative, I have to make it 0, right? Otherwise, intuitively, this is some projection, okay? This is what you do. And then what do you do after this? I can do gamma update here itself, right? I can do that.
Yes.
Yes.
What is this? Gamma k plus, oh man, I should not have
New
used this, right? So give me something else. Eta beta.
alpha
Okay.
delta.
Okay. Now we have alpha k gradient with respect to nu L of x capital T lambda k plus 1 nu
Sir, k, I guess, because if we
no?
do simultaneous update, I guess it gets unstable. Lambda k should be there, I guess.
Yes, sir.
Yeah. Okay, so this is k. I can do one more thing. I can do a loop of I can have two variables here and loop it, but that's quite complex, right? We will see what this is the algorithm that I'll get, right? So end for. Do you agree? You keep doing that until whatever k equal to 1, 2, etc. some t dash. Clear? And once you do this, hope for the best. That's all, right? That's all we know now, right? So we have to solve this. I for sure know that if I solve this, I'll get the optimal. But based on my intuition about simple gradient descent, I came up with this algorithm. But I have absolutely no clue of what whether this will converge. So okay, before that, so what are the questions that you can ask here, right? We proposed this algorithm. Let's look at it from both, let's say, a practitioner's viewpoint as well as from a theory viewpoint, right? What are the questions that we'll ask? Maybe I'll only ask specific people. Ritik Kumar, can you tell me what are the questions that will come to your mind with the moment you see this algorithm? Yes.
Right now, no question is.
Okay. Now, if you implement this, what is it that you expect? Okay. If I ask you to implement, what will you do first? If I ask you to implement, what is it? So you have to go code, right? The moment you start coding, what is the first question that you will ask? Are you from computer science or what is your background?
Computer science, sir.
Computer science. Yeah, you should be able to immediately tell me, right? You have taken so many courses. So what is the first question that you will ask? Can you code this first line?
Yes, sir. Yes.
This is easy, initialization.
Yes,
Can you write a for loop?
yes,
That
sir.
also you know.
No, I cannot understand your question. What you are asking? Like implementing this is not so tough, but
no, if you want to implement, you need to know certain things, right? So that's why I'm asking. So can you implement this step, gradient descent?
yes.
How will you implement? See, xt plus 1 is a variable. So xt you
Yes.
got it in the previous iteration.
Yes, sir.
What is the new gradient also you can find, right? So what is the next thing that you have to do? Can somebody else tell me what is the problem here?
How difficult is it to compute a gradient? Or how costly it is to compute a gradient?
We should find it
Let's
at
not go that deep into computer science, but well, let's assume that the function is very simple and you have a closed form solution, closed form for your gradient.
So it's like whether it converges and how fast does it converge, if it does.
Okay. Can somebody else tell me?
to find the eta t, sir, for every
Eta
step.
t, right? You don't know what eta t is. How do you find this? What is this eta t, right? That's one question that you will ask. All of you will ask, right? So how will you find this eta t now? That's the next question, right? What is it that you would do if you are a practitioner? Okay, so I'll ask maybe Kunal Kumar. Are you there?
Yes, sir.
So what is it that you will do?
So I will take some neighbor points and calculate the value and then proceed do the needful. So, or if there are some library, I believe there are some library I can use that also. So,
Library for what? Well,
so
okay, so you are not allowed to use any library. Let's go back in time to 1991. Okay, you are
yeah,
allowed to
in
use
that
write a
case,
C program. No libraries available for all these machine learning. So what is it that you will do?
in that case, I will find the value for the. I suppose. Uh,
See, how do you find eta t? That's the question, right?
So maybe brute force, like try out all the values and see which works.
Okay, so that's one possibility, right? You do brute
Yeah.
force, right? So what do
yes.
you think? What is your intuition? So if you were to write this, what is your intuition?
Even the like if I take very small eta t, let us say so,
Huh? Huh?
then it might take a lot of time to approach the optimum. If I take too large a eta t, it will overshoot possibly.
Okay.
So I need to have certain domain knowledge also for coming up.
Sir, I
Okay.
think best way would be just to analyze gradients of what order they are and what is
Mhm.
xt. How by what order do I need to change xt? And I
Huh?
guess by analysis we can obtain eta t.
Okay, so there are two ways. One is brute force, do a lot of experimentation with different kinds of eta t. One thing is clear, right? If eta t is large, then what will happen eventually? So you'll go here, and if eta t is large, then you'll probably end up here. And then if eta t is large, you'll go back and forth, right? It'll keep on oscillating between 2 points. It will not converge, right? Do you agree?
So we can even have eta t as a function of t. Maybe we can do
Exactly.
something like
Why I have
annealing.
written it as eta t. Yes, if it is a function of t, what should be the function, right? That's
So it's like
another question.
annealing.
Decrease.
Yeah, it's like exponential
Decreasing,
decrease
that's
or
very
annealing.
sure, right? Because you cannot, as in when you move closer and closer to the valley, you better take lesser and lesser steps, right? So meaning the step size should be smaller, as in when you move closer to the valley, right? Closer to this point. On the other hand, if you're far somewhere here, well, I can be a little more aggressive and take aggressive steps, right? So but the question is how one thing is clear from intuition, this could go to zero as t goes to infinity, right? I should take smaller and smaller step as and when I move further in time or iteration. That's very clear, but how should it go to zero, right? That's a bigger question. Now you can try out a lot of things, right? 1 by t, you can take maybe 1 by root t kind of a fall, or you can take depending on the number of steps. Suppose you are saying that I'm going to take totally t steps, I can take 1 by t steps or 1 by root t steps and blah blah blah, right? So many. And then for each one of them I can do, let's say, alpha 1, alpha 2. I can choose different coefficient, maybe 0.1 divided by t or 0.01 divided by root t, all kinds of combinations, and that's how practitioners do things, right? Of course, even theory will not help you much there. So it can at most say that you should take something like order of 1 by root t. It will not say how exactly you should move, but roughly order of 1 by root t. This is also good, right? For suppose theory says 1 by root t, all that you have to do is some constant by root t is what you have to take and tune this constant instead of tuning the order itself, like 1 by t, 1 by root t, t power 3 by 2, and so on, right? This is what theory will help to some extent, but after that, if in the real world you have to do a lot of tuning, right? Is that fine, everyone?
Yes,
Yes.
sir. So, can we use this? I mean, like, it's a very subjective question, but we can have the simulated annealing kind of scenario, or this cooling functions that are inspired from physics.
Well, for what? For the
Yeah,
order or
for
the
eta,
finding fee? Huh?
for eta can be some exponential cooldown functions that we observe in physics.
No, so I can. So basically, we will do some analysis and show that it should be of the order 1 by root t. But
Yes,
what
sir.
should be this constant is another question, right? I'm
Yeah,
not
yes,
sure if that kind of approach will give you this exact C. I'm not sure. I have to think about that. But The order you can prove without any of those things. We will see how to do that. Okay, but at least that's one question that you will ask, right? What should be the eta t? Okay, now the moment you get eta t, you will have the solution. You can write this code. What is the next question that you will ask? Well, whether it converges, right? That's another question that you should, whether the algorithm will stop. If it doesn't stop, then there is no point, right? And then the question is how fast it goes down to the optimal solution. These are some of the practical questions that you will ask. And it becomes very important in the current world because you know, you will do a lot of these things across devices and you have to do some sort of information exchange, and you cannot do it if the convergence is slow. You have to do a lot of exchange. That means you need a lot of bandwidth, lot of time, etc. So convergence becomes an important issue. Okay, is this fine? Well, if somebody don't understand this, don't worry about this. Okay, don't worry. Okay, let's look at another formulation of this. Okay, it's an interesting way of looking at this. Same problem, minimize f naught of x subject to the constraint that x belongs to some set C. Well, C is described through those inequalities and equalities. Okay, so now how do you solve this problem? I can do exactly the same thing. Okay, I'll write that. So first step, initialization. I'll take x1 as 0. Okay, this is the initialization step. Second, for t equal to, let's say I'm going to take totally t steps. For each of the steps, you do the following. What I'll do is, let's say I'll do this x t plus 1. Maybe I'll use some other variable, z t plus 1. Okay, is gradient descent, nothing fancy. Okay, minus eta t. Again, the question is what should be eta t here, right? Gradient of x of t. Is this fine? This is gradient descent. Now what's the problem? If I stop here and keep looping, what will happen here? What is the issue? Will it solve this problem? Can somebody tell me? So what I'm doing is I'm basically doing the gradient descent. What will happen? So I'm forgetting about the constraints. Can somebody tell me? Maybe Rijul, can you tell me what happens? Rijul, are you there? Yeah.
Sir, can you repeat one thing? Like we are forgetting about the constraint, then like.
What will happen to this? So suppose I do n for here itself. What will happen? I do this. I keep looping. What will happen? Let's say eta t is 1 by square root of capital T. I have given you that also. So you will just basically move in the direction of descent of f naught. So what might happen? Can you intuitively think and tell me the answer? Eventually, what might happen?
Sir, eventually the accuracy might increase.
Well, no, the question is whether we will go closer to the solution of this problem, this particular problem, or not.
Yes, sir, the accuracy to get the solution will increase. Like if there will be higher eta, then the solution will be, the difference in the approximation will be more the error.
Now, let's say you have this 3, whatever, I'm very, your constraint set is this. This is your C, for example. Now, what will happen if I start here and keep on going in the direction of descent?
So it will reach the
but
this point.
Is this the solution for this problem? If C is this?
No, sir.
What is happening now? See, it says you should stay within this C, right? That set. Think of it as a well, and you are trying to optimize over that well. So if you do gradient descent, you will move out of well, right? Out of the well. Sir. That's not the solution, right? So what should you do? Now what is it that you have to do? What is it that you will do? Suppose you are here, okay? So suppose you are here, okay? So what is it that you will do? So you have come out of the well is C. What is it that you will do? I cannot use this point, right? I mean, you are outside. So what should you do? Think of it as like the moment you are out of the well, or let's look at the other way. So this is some small island, and sea is your island, and around that there is water with crocodiles. So now you have to optimize something, and you found that based on gradient descent, it said, well, you go out of the well, you go out of the island, right? That means you have to go into the waters, right? So what will happen? Immediately the crocodile will kill you, right? So what is it that you have to do? What is it that you will do?
So like we'll decrease eta.
No, man. So okay, forget about all optimization, everything. If you are in the waters and there is a crocodile, what is it that you will do?
So run away.
Where will you run away? So of course, you cannot run. You have to swim. Where will you swim? You will swim
Away
towards.
from it. Away from it.
Oh well, the crocodile is coming here, let's say, and you will move in this direction into deep waters.
No, sir.
What is it that you will do? The best thing. It's a crude analogy, but best thing is what?
Yes.
Huh? If you are in the water, you cannot outrun the crocodile, right? For sure. What is the best thing that you will do?
So fight against it.
Oh man, don't. Okay. Anyone else can tell me the solution?
Get back to the island.
Run towards the island.
Huh?
Run towards the island.
Run towards the island, right? So this. Okay.
So there was
No.
island also. I thought
Huh?
there was water only.
No, there was an island, right? That's what I said. Sea is
Okay,
your island.
okay. Okay, there was island, then we can run towards it.
Yeah. So you have to run towards the island, right? What is this called? Okay, let me maximize the picture here. Okay, I'll write it like this. So this is your sea, and you have a point here, and I just ran towards the island. So I'll reach this point. So crocodile cannot come and kill. Assume that it cannot come into the land. So what is this called?
So the minimal point of the set.
The closest point in the set C, that is to the point where you are, right? So this and this are the closest points, right? This is also called what? Based on the, okay, so let me assume this.
Projection.
So the point and this,
Projection.
this is the close, projection, right? So all that you have to do is project, right? That's the best thing that you can do. So what do you do here? Xt plus 1 is whatever. I'll maybe use a different color to write projection. I haven't defined what projection is. Project onto the set C this particular point, right? What is that point? Zt plus 1. Zt plus 1 is like you are in the waters. You have to project. That means you have to go to the land, the nearest point in the land, right? So that will give me projection. So what is it that you have to do after that? You do n for. So keep looping this, right? The moment you go out of the land, you just project onto the land and keep doing that until some point capital T. Now, what is it that you will return? Yes, return what? You can either return x capital T, or again same thing we'll do, right? So the average, okay, and then you can also do.
Sir,
or
why does average work, sir? I mean,
what will happen eventually? So you will be closer and closer to. We will see why this average is required, but for now, this is what you want, right? Or if it is convex, nice. I don't
So if
care
it
about
converges, like if x converges to some value, then average works. If not, like we can't tell anything about it, right?
Hmm?
If x converges to some value, then average works.
Yeah.
And
So if T is sufficiently large, right? So if I look at the average will be close to x star. We will see why. Okay. For now, I don't want to confuse you. So essentially, forget about the average and forget about this also. I'm writing it for some other reason. So let's look at this also. I'll pick the best. Best also makes sense, right? Well, if you look at convex program, most of the times this best will be equal to xt itself. So you don't need to worry. So we'll only focus on this. Is that fine? Everything, this is fine? Everyone?
yes, sir.
right? This is how you can solve optimization problem. But the question now is, what is this, right? What is projection? See, if I figure that out, I have kind of solved my constraint optimization problem, which is equivalent to solving my Lagrange problem also. So either use this complicated beast here using Lagrange, right? Or you use this nice thing here, right? But still people oftentimes go for Lagrange because sometimes you have a closed form solution. There you need not solve, you need not have any algorithm. You can exactly say this is my solution, right? Is this fine? Everyone?
Sir, is it possible to repeatedly oscillate between projection point and outside point?
Repeatedly oscillate meaning? See, this is what you are doing, right? So you are taking a point, you go here, and then you move here, take project, you move here, project, you move here, project, you move here. Project. Hopefully, you know, after some point, you'll be inside. Okay, that's what we hope, right? Your question is valid, whether, you know, I'll keep on hopping out and back and forth, right? That's your question, right?
Yes, sir. Yes, sir.
It can happen, right? So for example, if you don't choose your eta t properly, you might hop back and forth and will never converge, right? It might happen. Okay, but you have to appropriately choose your eta t, and you know, you have to project. Okay, projection is a subroutine. So now let's see what is projection, right? What do you think is projection? So let's let me write this. So what is a projection? So I have a set C. If I have a point, let's say y, what do you mean by projection? Can somebody tell me? Why is this not a projection? So suppose I have a point here, okay? Is this a projection?
So it has to be at minimum distance from,
Right.
like for all x belongs to C, this
So it should,
norm of x minus y should be less or something like that. Yeah.
Yes. So
So-
somebody else was saying, huh? Yes.
so it should be like it should be perpendicular to the tangent on the surface.
Well, yes, but that is true. But a simpler characterization of this is what? You take x in C such that x is the closest point to y in C. Do you agree? If we take any other point, you know, it's farther away from y. X is the closest point to y, which is in C, right? How do I write that? So what is close? So for example, you take this x minus y, look at the 2 norm, let's say the distance, right? So I want to pick an x that is closest to y in C, right? So now I can define projection as follows, right? Well, C is convex, okay? Otherwise it doesn't make sense. Okay, we'll see why. Okay, so projection onto C of y is defined as, you take minimal, you look at the distance x minus y, 2 norm, you pick all x that is in C such that x is close to. Well, now this is what projection is. Can you go back and see what's the problem now? See, if I want to implement, this is
So it's
easy.
again one unconstrained problem. Like we've come up
It's a constraint optimization problem, right?
Yes.
Now, what do you think is the issue? So, well, I can call a projection subroutine. Maybe somebody would have written a projection subroutine. I can call that. But then, if somebody wants to write that projection subroutine, then again you are stuck with the same problem. I mean, this is another convex optimization problem, right? Now, how do you solve this guy? This guy again, it looks like you are in circle, right? You go in circle, right? You agree? You go back and forth. Do you agree?
Yes.
Again, you know, if you want to solve that, your f naught will be norm, and again x belongs to C. You say again project, but then okay. Now, how do you solve this problem? Maybe you can go back to this, right? So maybe the projection problem is quite simple. Maybe you go to this, or the projection problem may be simpler for certain class of problems. Let's look at one problem. I'll give an example for which maybe in the next class I'll continue with this, for which we know how to solve this exactly. Okay, so what is this projection problem? what is it that I'm doing? So I'm trying to minimize this. X belongs to, I can also take square if you want, right? X minus y square. So let's look at C to be this. Okay, it is all those X such that A transpose X less than or equal to B. X is in Rn. Okay. Now what will happen to the projection problem? So it will be this, right? Minimize overall X, norm of X minus Y, I can write it as X minus Y transpose X minus Y, right? This is nothing but norm, subjected to the constraint that A transpose X less than or equal to B. So what is this constraint set? A transpose X less than or equal to B? Geometrically.
Intersection of half space, basically.
Half space, right? So you're basically projecting a point onto the half space. What do you think is the solution? So let's look at intuitively, right? So this is what you have, half space. Suppose you have a point here. So what is the projection?
Perpendicular.
Yeah, it's very easy, right? It will be perpendicular to this. Okay, this will be the. What if your X, Y is here? What is the projection?
That point.
Projection of Y onto C is Y itself,
Y
right? Because you are already inside the land. Why do you want to run away from the crocodile, right? So intuitively we know the solution, but how do you solve this? Okay, now step one. So this is the projection problem, right? So this gives you projection of onto set C of Y, right? This is what it will give. So what is it that you will do? I'll leave this as an exercise. So essentially you do Lagrange and solve. Okay, you will get exact solution. This will be a homework problem for the next class. Okay, before that I want you guys to solve this problem and come. I'll solve that in the next class. Is that fine? Pratik, so here is one case where you can exactly solve.
Okay.
Okay.
Yeah.
For this problem, if your constraint set turned out to be A transpose X less than or equal to B, then I know how to do projection, and therefore I know how to implement this algorithm, right? Keep iterating, and I know how to write a projection subroutine, which is simple, very simple. So I can implement this algorithm. Hope that it solves the original problem. Okay.
Yes. Yeah.
Okay. Yeah.
So if it holds good for this half space constraint, then it should hold good for polyhedra also, right? Like
You are saying if you, yes, so you have, let's say, another which is like A dash transpose X less than or equal to B dash. If that is your another constraint, then yes, true.
Yes, sir.
Okay. Okay.
Yes,
is that
sir.
fine? Okay. Any other questions? So maybe I'll stop here, and next class I'll continue. So I overshot by 10 minutes, but yeah. So if you have any questions, So we will solve that constraint optimization problem, and we will look at one of the oldest ML algorithm called perceptron, and see how it can be viewed as some sort of a gradient descent with certain objective, and try to understand what is known as stochastic gradient descent through that example. Okay, and also the notion of online learning through that example. Okay, is that fine, everyone?
Yes, sir.
Yes, sir.
Mandeep?
Yes, sir.
Yes. Mohan Sai Krishna?
Yes, sir.
Okay. Others? Siddharth?
Yes, sir. Yeah.
Okay. Okay. Fine. Then I'll stop. We'll meet in the next class. Okay. Okay. Thanks. Okay. Anurup, I'll join the other call. I mean, the other link.
Yes, sir.
Okay.
Yes, sir. I'll open that. Yeah.
Okay. Okay. Thanks. Bye. Hey, bye, Savan.